And
Allumage
liftoff.
UAP, décollage.
Decollage, liftoff from a tropical rainforest to the edge of time itself. James Webb begins a voyage back to the birth of the universe.
Christmas Day 2021. A date that will go down in history, and not just because of the holiday. On that day, while many of us were eating, giving and receiving gifts, and spending time with our families, the good folks over at NASA, the ESA, and the CSA were hard at work, delivering their ultimate present to humanity. A groundbreaking next-generation telescope capable of looking backwards through time. The James Webb Telescope, NASA's most powerful observatory ever, which launched from the ESA spaceport in French Guiana, packed inside an Ariane 5 launch vehicle. From distant stars and planets to the dawn of time itself, this telescope will transform our view of the universe in every direction it is pointed. And with its launch, it beckons in an exciting new age of astronomy along with it. The age of Webb. The James Webb Telescope is the product of an international collaboration between NASA, the European Space Agency, and the Canadian Space Agency. It is the official successor to NASA's Grand Hubble Space Telescope, which fundamentally changed our understanding of the universe, but is now in the twilight years of its operation. The James Webb Telescope is larger, more efficient, and simply far superior in almost every respect. Each element intricately designed using innovative breakthrough technologies. Webb has been in development for more than 30 years, worked on by hundreds of thousands of scientists, from over 250 universities and institutions, across 29 US states and in 14 other countries. Naturally, it is the most complex and expensive telescope ever constructed, and ranks as one of the most ambitious yet risky space projects ever. It has cost around $10 billion to construct, and was delayed by nearly 15 years. But now it is finally up in the sky. All its delays, plans, rebuilds, and tests have been completed, the telescope blasted off from Earth successfully, and it is now currently preparing itself in space for the first part of its mission. The James Webb Telescope has three main objectives. The first is to look all the way back through the universe, towards the light of the very first stars. The second is to peer into extrasolar planetary systems, looking for worlds with atmospheres suitable for life like us. The third is to expand on and complement existing research into the evolutionary processes of the universe, how galaxies, stars, and planetary systems come into being, as we tirelessly attempt to make sense of our cosmic origins. Discussions regarding a successor to the Hubble telescope began before the latter had even gotten off the ground. Scientists had a mind to build a high redshift infrared observatory capable of seeing the most distant galaxies in the late 80s. Some years later, in 1996, NASA commissioned the Next Generation Telescope project. But this would later be renamed as the James Webb Telescope, in honour of the late former NASA administrator during its successful Apollo program, James E. Webb. Moving into the 21st century, NASA contracted several private firms to research new technologies for their next great observatory. They investigated new materials to create a larger and stronger but lighter telescope. They looked for ways to keep that telescope cool, so as to minimise background interference. And they researched how to create a fragmented primary mirror, one with a significant overall aperture, but that could be divided up into segments and folded to fit inside a rocket. An overly optimistic launch date for the telescope was set at 2007, but as we now know, the telescope would undergo almost 15 years of delays. In the early 2000s, various factors culminated in the project vastly overrunning its schedules and budgets, and costs began to spiral. A thorough review and replan of the telescope's development in 2005 found costs to be close to $4.5 billion, significantly more than the $800 million originally earmarked in the project's primary contract. The telescope's development regime was completely redrawn, and multiple approved delays pushed the launch date forward to 2011 and 2013 respectively. By mid-2007, all of the new technologies required to achieve the observatory's technical objectives had been developed. After the telescope's design was finalised, it then had to undergo various intensive critical design reviews, each identifying their own issues and continuing to kick the can down the road. Before long, the launch date was pushed back until at least 2015, but as late as 2018. The telescope's construction and assembly was completed by late 2016, but the rigorous testing phase of the final product was still yet to come. In March 2018, NASA announced yet another long delay to the launch, as the telescope's Sunshield unit had ripped during a practice deployment. A follow-up review then returned more than 340 unresolvable errors, which would result in a mission failure in space, and thus the launch date was again pushed back, this time to 2020 and then to 2021. By this time, the project had run up a total cost of more than $8.8 billion, with more inevitably required to maintain the observatory after its launch. But ultimately, NASA was backed with the resources it needed to see the project through. And in September of last year, the completed telescope was shipped from its testing facility in California to the Guianan Space Center in French Guiana, aka Europe's spaceport. It was packed into a launch configuration and attached to one of the ESA's Ariane 5 launch vehicles. Liftoff was delayed by a further few weeks, but the telescope did finally blast off from Earth on Christmas Day 2021, more than 3 decades after discussions surrounding its development had begun. Webb's extensive delays and costs, while painstaking for astronomers, were not in vain. Risk has been managed incredibly effectively when considering the number of earth-shattering paradigm shifts required for this telescope to be a success. The most iconic innovation is, of course, the telescope's fragmented, honeycomb-shaped primary mirror. Traditional telescopes like Hubble have one solid primary mirror of a certain size and mass, which is constrained by its ability to fit inside its rocket. James Webb's primary mirror, on the other hand, is made up of a brilliant array of 18 hexagonal fragments, working together as a single mirror, shaped as such because of their 6-fold symmetry and ability to fold together inside without leaving gaps. This allowed scientists to pack up the mirror into a launch configuration small enough to fit aboard the rocket without compromising the aperture. When unfolded and in their operational configuration, these fragments combine to make an enormous mirror, extending some 6.5 meters across. This gives it a comfortable 25 square meters of clear aperture. Compare that to Hubble's primary mirror, which has an aperture of just 4.5 square meters, and you can see how much difference this stands to make to our observations. Just as the primary mirror had to be compact enough for its launch, it also needed to be light enough. If we were to scale up Hubble's primary mirror to Webb's size, it would be far too heavy to be launched from Earth, never mind being too large to fit inside the rocket. Therefore, another paradigm shift implemented in the mirror's design came in the materials it is made from. Webb's mirror fragments are made from beryllium, a light but strong material 10 times less massive per unit area than Hubble's mirror. Each hexagonal segment weighs around 40 kilograms in total, and the overall mirror weighs less than its predecessors, despite being 6 times larger in aperture. These mirrors are also coated with a microscopically thin layer of gold, which aids their ability to reflect infrared light. That's what the James Webb Telescope is, an infrared observatory, which surveys in a broad range of wavelengths from the near-infrared to the far. When it comes to peering into the most remote corners of the universe, infrared light is our tool of choice. Most objects cooler than stars emit radiation most prominently in the infrared wavelengths, and in addition, this kind of light suffers less from the effects of extinction as it travels through intergalactic mediums. And, for the very distant objects, their light has been travelling through the ever-expanding universe for so long that those waves have been redshifted out of the visible spectrum and into the infrared spectrum, rendering them invisible to non-infrared telescopes. And so, an infrared observatory is what we need if we're going to try and image the farthest galaxies. However, maintaining such an infrared observatory is more challenging than for other kinds of telescopes, because infrared instruments need to operate at extraordinarily low temperatures if they are to survey a broad enough range. The Hubble telescope was fitted with an infrared sensor in 2009, and while it did reveal a host of previously undiscovered, extremely remote galaxies, it could only see a limited range of frequencies in the near-infrared. The longer wavelengths in the mid and far infrared, where the very oldest galaxies are thought to be hiding, are drowned out by the excess heat from Hubble's own optical instruments. Hubble's mirror operates at a temperature of around 23 degrees Celsius, and even at that level of heat, the infrared excess produced by the telescope blinds its infrared sensor to most of the wavelengths required for seeing the oldest galaxies. And thus, another big technological leap Webb had to make was being able to operate at exceptionally low, cryogenic temperatures. The telescope's optical unit is fitted with a number of infrared cameras and spectroscopic instruments, which all need to be kept below 50 Kelvin. In fact, the mid-infrared instrument, which measures waves between 5 micrometers and 27 micrometers, needs to stay even colder, at a temperature of just 5 Kelvin. And as such, it is fitted with a helium gas cryocooler. The remainder of the instruments in the optical unit will stay cool thanks to the telescope's tennis court-sized, diamond-shaped, multi-layered sunshield. This shield is responsible for blocking and reflecting excess heat from the sun and the earth, which would otherwise blind the infrared instruments. It consists of 5 ultrafine layers of the polyamide Kapton E, each coated with aluminium, with added layers of silicon on the outermost sun-facing sides. On the Earth-facing surface of the sunshield, the temperature will be around 383 Kelvin, as it bears the full brunt of the sun's enduring gaze. But by the inside of the 5th layer, on the telescope-facing side, the temperature falls to as low as 36 Kelvin, a level sufficient for minimizing background light. This sunshield will need to face both the Earth and the Sun at all times, and it will achieve this by orbiting well beyond the Earth, whilst hitching a ride from its gravity. Webb is now positioned in a point of suspension more than 1 million miles away from the Earth, known as the second Lagrange point, or L2 for short. L2 is a zone of equilibrium between the Sun and the Earth's gravity, and anything in this zone is dragged by the Earth as it orbits the Sun. Stationing Webb here means that the Sunshield can consistently block both the Sun and the Earth, while not falling out of sync with Earth's orbit. Webb will be maintained in this zone via a series of manoeuvres, thrusts and course corrections as it drifts in a halo-shaped orbit in L2, keeping it tethered to the Earth like a dog on a leash. And so, in addition to allowing the telescope to remain cool, another advantage of this orbit is that the telescope never strays too far from Earth, and its measurements always beam back in a timely and predictable fashion. But despite this circumstellar orbit will mean that Webb will be unreachable for repairs after its launch, for all intents and purposes. We may be able to ship things to its general location, but the instrument-changing work performed by the hands of astronauts, which made Hubble such a long-lived success, is off the table here. Thus, there was a lot more riding on this telescope's launch proceeding perfectly, with everything having to go exactly according to plan, hence the rigorous testing regime and 15 years of delays. Thankfully, these patient efforts seem to be paying off in real time, as both Webb's launch and its initial deployment phase have now completed, concluding an extremely nervy fortnight of terror for scientists and enthusiasts alike. Webb was folded up, Sunshield and all, into a neat cube-shaped configuration. In space, the telescope had to unpack itself like a transformer, or a giant piece of origami, to reach its operational configuration. Only half an hour after launch did the telescope separate from its vehicle, and less than 2 minutes later, communications had been established and the energy-generating solar panels had unfolded. Only a very specific velocity would allow the telescope's trajectory to guide it to its desired location in L2. And so, Webb was deliberately launched much slower than this required velocity, and would undergo 3 engine thrusts on its journey to speed up to the level needed. Reason being because it is easy to turn on the engines and speed up the telescope, but near impossible to slow it back down thereafter. Around 13 hours after launch, Webb underwent the first of these 3 course-correcting thrusts. Its engines switched on for more than an hour, giving the craft its first kick towards its destination. About 1 day after liftoff, the telescope's antennae had been deployed, including the high-rate antenna, which will transmit just under 30 gigabytes of data back to Earth twice a day. Just over 2.5 days in, shortly after the telescope had passed the Moon's orbit, the engines switched on for another 9 minutes during the second course-correcting thrust. This was followed by the unfolding of the pallets containing the Sunshield segments, and 2.5 days later, this 70-foot Sunshield began to deploy. It was one of the most complicated and nerve-wracking parts of the deployment. The super-thin layers had been folded no less than 12 times to fit inside the rocket, and took a full 5 days to be extended, separated and tensioned correctly. The Sunshield deployment concluded on the 4th of January 2022, allowing the optical telescope unit to begin assembling, another mission-critical and complex process. The outlying beryllium hexagons of Webb's primary mirror unfolded and aligned themselves with the rest of the unit, taking around 4 days to complete. And so, on the 8th of January 2022, the most perilous part of Webb's journey was complete, and the 2 weeks of terror for the astronomical community was brought to a satisfying conclusion. There was still much more to do, however, to prepare the telescope for its mission. On the 24th of January, Webb completed its final engine thrust, lasting 5 minutes, giving it one last push towards its destination in L2, where it is now parked in its halo-shaped orbit. Due to the observatory becoming hot during its launch, it will need to cool down in the Sunshield's shade for at least 3 months. During this time, extensive calibration and testing of the telescope's equipment will take place, as the instruments are tuned and readied to snap clear images. It is hoped that Webb can begin its first cycle of observations around 6 months after its launch, but it could take another month for those observations to be processed and made available to the public. So we're probably looking at the middle of this year before we can expect the first mind-blowing images. But once the telescope is fully operational, the nominal part of its mission will begin, and is expected to last at least 5 years, and there is hope that intuitive engineering and efficient fuel consumption could extend its life to around 10, or perhaps even longer. So, from mid-year this year, we can look forward to a new age of fascinating discoveries lasting at least a decade. We stand to finally uncover some of the universe's best-kept secrets, to understand our place in it all better than ever before. And all of that will begin by looking back to the beginning of time. As mentioned, Webb has 3 key objectives: to study the evolution of the universe, to search for signs of habitability, and most importantly of all, to shed light on the cosmic dawn, the moment when the very first star illuminated an otherwise dark and desolate universe. We believe that the universe was born from an event known as the Big Bang, and for just under 380,000 years, it was filled with a great luminous ocean of plasma. When this ocean disappeared, the universe entered its first dark age. For hundreds of millions of years, there were no light-emitting sources in space, and anything in the universe back then would have simply seen nothing. But within this blanket of darkness, newly formed hydrogen atoms created by the ocean were starting to interact with each other. Over time, various natural forces led to those atoms accumulating into giant clouds of gas, colossal asymmetric mounds of scattered atoms capable of localized interactions. Pockets of more concentrated matter within these gaseous mediums were breaking off from the rest of the cloud and contracting, leading to smaller, denser concentrations. Inside these compact cloud fragments, the compression grew greater and greater, and the atoms within became more energized. Initially, tremendous amounts of heat were generated within the darkness. But then, something not seen for hundreds of millions of years followed: light. Suddenly, one concentration of atoms became so massive and compressed that it turned into a spherical ball of plasma, which radiated high-energy photons from its surface. The first star was born, and light once again lit up the universe. Before long, large numbers of these earliest stars had ignited, giant spheres of pure, untapped hydrogen and helium plasma, producing enormous amounts of energy, but remaining intact due to the gravity of their sheer mass. The cosmic dawn had come, and the stelliferous era of the universe had commenced. sometime between 200 and 500 million years after the Big Bang. During this post-dark age, the universe was filled with these ancient stars, known as population 3 stars. They are believed to have been highly volatile and inefficient, leading short, turbulent lives which ended in violent supernovae. But during their energy-generating cycles, they are believed to have synthesized the universe's first elements heavier than hydrogen and helium, before releasing them and enriching the gas around them. Over time, large numbers of these stars found each other in space, the force of gravity binding them into clusters containing thousands, intersected by abundances of the gas left over from the Big Bang. This is how we believe the first galaxies formed. Large groups of stars began accumulating into small and torrid but productive dwarf irregular galaxies, which would in turn become cradles for new generations of more stable stars. We've never seen a population 3 star. No telescope we have launched to date has come close to the sensitivity or range required to see these old beasts in all their glory. But Webb's unparalleled large mirror, coupled with its extensive range of infrared coverage, may be able to reveal these Genesis stars and galaxies to us for the very first time. Because light's speed is limited to about 300,000 kilometers per second, the further away we look into space, the further back we are looking in time. Hence we use light year as a unit of measurement. But this particular age of the universe, around 13.5 billion years ago, is one we've struggled to shed light on so far, as the ancient light from this age has taken its vast cosmic journey towards Earth. The expansion of space has redshifted it out of the visible wavelengths and into the mid and far infrared. But as we covered earlier, conventional telescopes like Hubble have mirrors too small and operate at temperatures too high to allow them to see this particular range of frequencies. Webb, on the other hand, will operate at the low temperatures necessary to bring these galaxies out of the shadows, and its significantly larger mirror will allow us to peer much more deeply into these infant galaxies than ever before. With all this scientific knowledge up for grabs, it's easy to see why studying the cosmic dawn is the primary mission of Webb. But it will also look for things much closer to home. Webb's giant primary mirror and infrared sensors will make it an excellent tool for studying the outer reaches of the solar system, a place shrouded in darkness in the visible wavelengths, but glowing in the infrared. The telescope will be used to peer into the icy reaches of the Kuiper Belt and Scattered Disk, two circumstellar bands of debris left over from the solar system's formation, which thus haven't changed much in the 4.5 billion years since. This makes them effective time capsules for studying the properties of protoplanetary material back then, which in turn will help us to better understand the mechanisms that gave rise to the solar system. Another one of Webb's principal objectives is to search for worlds beyond the solar system, around other stars in the Milky Way. Webb will expand upon the work performed by missions such as the Kepler spacecraft, an observatory which made use of the transit method to identify exoplanets. Transit observations can be made when an exoplanet passes in front of its parent star relative to the Earth, blocking out some of that star's light in the process. We can then measure this flicker in the star's light curve to reverse engineer some of the passing planet's properties. While it may sound like simply chasing shadows, it's actually one of the most reliable means we have of identifying exoplanets, contributing to the discovery of thousands throughout the 2010s. And Webb will take this a step further, able to zoom in on the starlight passing through the atmospheres of such transiting worlds to deduce their chemical properties. The goal is to identify signature molecules which may indicate habitability, like water vapour, in these atmospheres. It's unlikely that Webb will be able to confirm the existence of another living world, but if it uncovers scores of Earth-like worlds with habitable properties, then it will become even harder to argue that life is a phenomenon exclusive to this planet. Webb's final objective is to aid science's ongoing efforts to study the evolution of the cosmos. Its infrared eyes will give us a new perspective on stellar nurseries, the nebulous birthplaces of new generations of stars. We've all become accustomed to the beautiful images of opaque, reflective nebulae snapped by Hubble, but Webb's infrared cameras will be able to stare right through them, revealing much more about the inner workings of these stellar incubators. This will be vital for learning how heavier elements, such as carbon, oxygen, and silicon, elements necessary for life, become incorporated into the birthing of new stars. Webb will also study the evolution of space on a larger scale. One of Hubble's greatest achievements was the world-famous deep field images, which show thousands of galaxies at every stage of the universe's life. Some 12 billion years of history in a single photo. Webb's unrivaled infrared coverage will help us to enhance the deep field images, rolling back the curtain of darkness to bring thousands more galaxies into view. From there, the rest of Webb's operational time will be divided up and allocated among projects pitched to the Space Telescope Science Institute. It may be used to solve currently unsolved anomalies in astronomy. For example, by looking into the KIC 846 system in order to find out what is causing its unique transit dimming. People have speculated everything from a dust cloud to an alien megastructure. Perhaps Webb will be the telescope to find the elusive Planet X, a hypothesized 9th planet in the outer solar system, lying far beyond the orbit of Neptune. The hunt for such a planet was catalyzed by observations of a strange gravitational influence acting on the Kuiper Belt. But the relentless search for this dim and distant hidden world has so far come up short. Perhaps Webb will be able to catch its outline as it transits in front of a star under observation. With all that in mind, we can be confident that this is the start of an exciting and unpredictable age in astronomy. Webb will revolutionize our understanding of the cosmos everywhere it looks. Once we get those first photographs later in the year, the floodgates will have opened. Every beautiful and bedazzling Hubble image destined to be blown out of the water by breathtaking new observations. There is so much to look forward to, both this year and in the long run. It's a pretty strange feeling, because often on this channel we talk about discoveries made decades ago. It can sometimes feel like we were born too late to uncover the same kind of mind-blowing discoveries that characterised 20th century astrophysics. But now that feeling is no more. This time, that you're sitting in right here, right now, is a significant period in history. For hundreds of years, people will look back on Christmas Day 2021 as the start of the new age in astronomy.